Chapter 2 Chemistry of Life, Part 2. Everyone who drinks of this water will thirst again, but whoever drinks of the water that I will give, him shall never thirst. John 4:13 through 14. Previous scripture is the perfect segue into our discussion that we're about to have regarding water. Hydrogen bonds that hold water molecules together give water very important and unique properties. The bonding of water gives it several unique properties. These properties include the list that we see here. Properties of it being cohesive. Water is adhesive. It can serve as what's called a solvent, and we'll talk about what a solvent is. Water actually is very important in regulating temperature. It expands upon freezing, and it also participates in a multitude of chemical reactions. Here's a brief presentation that's embedded within this particular presentation that talks about what happens if we don't drink enough water. So let's talk about the first property of water from the list, and that is the fact that water is cohesive. This property of cohesion actually has to do with the fact that water molecules will stick to other water molecules. This property of being able to stick to itself, water sticking to itself or other water molecules, also gives it a unique property called surface tension. This surface tension actually is almost like a thin film across the top of water that actually will allow certain insects to walk or glide across the top of water. The property of surface tension that's conferred by cohesion, in other words, water molecules sticking to each other in order to form a film, if you will, may be best explained in this video that's embedded that you can click on to listen to. The next property of water that we'll discuss is adhesion. Water is adhesive. In other words, water molecules also can form hydrogen bonds with other molecules that are not water. So water sticking to itself or to other water molecules is called cohesion or the cohesive property of water. But water being able to actually bond to molecules other than other water molecules is actually exercising the property or displaying the property of adhesion. So, in other words, water is adhesive. So, when we spill water on the countertop, per se, and we actually are able to wipe up or absorb that water with a paper towel, absorbing the water with a paper towel, so that water actually, those water molecules binding to molecules of a different substance, something other than water, that is the property of adhesion. So, that property of water being adhesive. As we go throughout the semester, the recurrent thing that we're going to see in this class is that there is a cycle to almost everything in life, as well as how life interacts with its environment. Well, water is no different. There is a water cycle, and this water cycle, per se, describes the continuous movement of water on, above, and below the surface of the earth. There are different components to this water cycle. First, evaporation. Evaporation is just the process of liquid being converted to gas or vapor. So when water evaporates, it's now a gas. Those water molecules are now in a gaseous form. Transpiration is a process of water moving to the top part of plants and evaporating. So basically, transpiration is also a form of evaporation, but it's specifically applied to evaporation in plants. The next component of the water cycle is condensation. So the process where water vapor becomes a liquid. So what happens is during that process of evaporation and these molecules are now separating and spreading apart and becoming a gas, at some point these molecules now enough of them can exist in the atmosphere and they can recollect based upon cooling down and condense and reform into a liquid. Now, when enough of these molecules reform from the gaseous form or takes on a new form in terms of becoming liquid again via the process of condensation, now those water molecules in the atmosphere can return to the earth in the form of precipitation, which is the next stage of the water cycle. Precipitation is when water that forms in the atmosphere now falls back to earth. Understand that precipitation can take on various forms. It can take on the form of rain, sleet, snow, hail. So again, water is constantly recycled throughout our environment, and we see it taking on different forms. You may remember the states of matter: solid, liquid, gas. So that's basically what we're seeing in terms of the water cycle. You will have the liquid form of water, and water in its liquid form is bound a certain way. The molecules are bound, a certain way. But then as water molecules are heated, now those bonds that hold them together, hold the water molecules together, will start spreading out and separating. And now you get this evaporation or development of gas or water vapor, which is what water vapor is. It's a form of gas. But when that gas or water vapor is in the atmosphere, once those molecules now begin to cool down and reconnect, and now the bonds draw closer together again, this process of condensation is just a reformation of water from that gas, from that water vapor. And when enough of that condensation occurs, or the reforming of bonds of water into the liquid form or to a form that creates a liquid, when there is enough of that accumulation or condensation, now we can have water returning to the earth in the form of precipitation. And as previously stated, that precipitation can be in the form of rain, sleet, snow, hail. So many of us are familiar with the word solution, but let's specifically define chemical solution. A solution is a special type of homogeneous mixture composed of two or more substances. Now, the word homogeneous needs to be taken note of, because what that indicates is that the concentration of this liquid, now that we're talking about the solution, is going to be equal throughout the entire solution. There's equilibrium in terms of pH balance, etc., or concentration of the particles throughout the solution. When we're talking about a solution, there are different components of a solution. You have what's called the solute, and that's the substance that's being dissolved into another substance called the solvent. So usually your solvent is going to be the liquid portion in which the solute, which may be a solid particle or solid substance, which is being dissolved. So let's take, for instance, as an example, let's say we're going to dissolve some sugar in a glass of water. So we take say a teaspoonful of sugar, a glass of water. Those sugar granules are your solute. That's the solid substance that's being dissolved, that we want to dissolve. The water now is serving as what's called the solvent. So the solute is being dissolved in the solvent to create this homogeneous solution where the concentration now of this mixture has equilibrium in terms of its pH, the number of particles, of how they're distributed throughout this liquid solution. So water is a solvent that's used to dissolve a lot of different solutes. Water, though, dissolves particles or solutes that are what's classified as being hydrophilic or polar molecules. This word hydrophilic, and let's just kind of look at hydro, the first portion of that word, or first part of that word, refers to water. The second part, philic, Philic, loosely translated means love of, so a love of water. So there's a term that states like dissolve like. So in other words, if you have a solvent that is polar, in other words, it has some opposing charges in it, then it is going to dissolve solutes that also have similar electrical composition in terms of electrons and protons, etc. So like dissolved like. If you have a substance that is nonpolar, so in other words, you don't have these opposing charges on them within the molecule, then you would need a nonpolar solvent. So in a solution, the solutes are dissolved in the solvent. The polarity of water, and polarity just means that it has positive and negative charges because, water is made up of H2O. There's a positive charge on the hydrogen, negative charge on the oxygen, and these charges are conferred based upon protons and electrons. The polarity of water molecules helps water dissolve most biologically important molecules. So, in other words, like dissolves likes. So, many biological molecules that we have within our bodies, which we will call biomolecules, BIO molecules, a lot of those biomolecules are polar in nature. In other words, they have both positive and negative charges as part of their molecular makeup and therefore can be dissolved in water. Since water is capable of dissolving so many types of molecules and macromolecules, it is termed or given the nickname of universal solvent. So that nickname, universal solvent, that is applied to water is indicating that water can be used to dissolve so many things that it's used universally across the board to dissolve many types of solvents. And again, I said solvents, but I meant to say solutes. Water is a universal solvent that can be used to dissolve many types of solutes. And again, just to re-emphasize definition of words, hydrophilic, so loosely translated water loving. Um, Anything that is hydrophilic is easily dissolved in water. It has polarity in its charges. So, in other words, it has positive and negative charges within the molecules that make up whatever that substance is. And we see that, say, for instance, in sugars and salts, etc., in various ions, you're going to have positive and negative charges. And again, I don't want to get deep into the chemistry of this. We're just trying to get a little superficial knowledge so that we can start tying things together and kind of have an understanding of how various molecules and substances within our environment as well as within our body interact and how various processes move forward. Now, I just stated that hydrophilic means water loving, and as a result of that, water being the universal solvent, and the concept of like dissolves like, on the opposite end of that spectrum, you have molecules and substances that are nonpolar, so they are uncharged. And we say that those substances are hydrophobic. So, in other words, they will not dissolve in water. So, hydrophobic, so if you have a phobia, PHOBIA, of something, if you have a phobia of something, it's like a fear of something. So, a fear of water, hydrophobic. So if you have a molecule, a substance that is hydrophobic, in other words, nonpolar, it doesn't have any charges on it, then that substance will not dissolve in water. It will require a nonpolar solvent. Examples of hydrophobic molecules or biomolecules are oils and grease, for example. So if you take some oil, you take a tablespoon of oil, you put it in a glass of water, you'll notice that the oil will float to the top because, again, the charges don't agree with, if you will, are not compatible with the charges in water. So water is not the best solvent for grease or various oils. You would need some other type of solvent that is nonpolar in order to readily dissolve these nonpolar or hydrophobic molecules. And this slide is just basically giving you a look at just a different perspective or a different look at this whole concept of polar substances and nonpolar substances and whether or not they will dissolve in water. So you've got polar substance in water to your left, a demonstration of that. So sodium and chloride, which is just basically table salt, NaCl, Na plus Cl minus, the negative charge is on the chlorine. And they're attracted to the charged regions on the molecules of polar solvents such as water, as opposed to nonpolar substances to the right, fats and oils, that they will remain separated from molecules of a polar solvent such as water, and therefore not dissolve as readily as a polar substance. And this slide just gives you a different perspective of what I talked about in terms of, having a solvent and a solute. The example that I actually gave you was sugar. This example is salt, but it's the same concept. Your salt in this particular case will be your solute, and water is going to be your solvent in order to dissolve now this polar substance, which is salt. So the slight negative charge on water attracts the positive charges on sodium, the Na plus sodium, which is one of the molecules or one of the elements that we will see in salt, table salt, because the chemical formula of table salt is sodium chloride, so NaCl. The slight positive charge on water attracts the negative charges in the chlorine because the chlorine is negatively charged. Now we can have a binding of the various compatible molecules, and a solution is formed because of the binding of these various molecules based upon their charges, their chemical charge. Water is also very important in the regulation of temperature. The regulation of temperature in the environment, but as well as temperature in our body. Water actually has what is called a high heat capacity. So, in other words, water can absorb a lot of heat before its temperature rises, which works out for us because if you've ever gone to the beach and let's say it's 100 degrees outside, but then the water is not 100 degrees, which would be boiling because you wouldn't be able in order to stand it. Water has a high heat capacity, so it can absorb a lot of heat before the temperature of water actually rises. And that heat has to be distributed over the entire body of water, be it the water in, say, the ocean or a lake, or even when you're boiling water in a pot. Before that water starts to boil, a lot of heat has to actually be applied to it before that temperature rises because of the heat capacity and the ability of water to absorb a lot of heat before its temperature actually elevates. Hydrogen bonds in water actually resist changes in temperature. So, an increased amount of heat is needed in order to increase water's temperature and to break those hydrogen bonds in water. And it is that elevated temperature and the breaking of those bonds that eventually leads to water boiling. And now those bonds are broken and you have the conversion of that liquid water into water vapor, steam, etc., as a result of those molecules moving rapidly around because the bonds have been broken. In coastal climates, you see more mild temperatures, and another characteristic property of water is that upon freezing, water actually expands. This, again, is tied into how these molecules are bound together and the rearrangement of those bonds based upon temperature. So when water freezes, the bonds between the molecules are broken. Those hydrogen bonds are broken, they're reformed. And when they are reformed, now the molecules are spread out as they freeze. This is why ice is actually less dense than liquid water, therefore it's lighter, if you will, and now has the ability to float on water, even though ice is just frozen water. But because of now this crystalline formation that's a result of how the bonds now are rearranged due to the temperature. You have a different composition, if you will. Another important property or characteristic that water possesses is that it is very important in carrying out chemical reactions. There are various types of chemical reactions and biochemical processes that occur within our bodies, and water plays a vital role in it. Two reactions that I'm going to bring to your attention look at point number two, hydrolysis and dehydration. So hydrolysis is the breakdown of something by water. Hydro being water, lysis meaning a breakdown or a splitting of something. So something is broken down or split by water. Dehydration means that water has actually been taken out of a particular substance. So we see water being removed from certain, substances. This process of the removal of water is called dehydration. So just to recap up to this point, the various properties of water is that it is cohesive, meaning water molecules will stick to other water molecules. It is adhesive. Water molecules will stick to other types of molecules other than water. Water can serve as a solvent. So, in other words, solutes can be dissolved in water. And we now know that water is given the nickname of being a universal solvent since so much can be dissolved in water. Water is important in regulating temperature. Water expands upon freezing. And lastly, the last concept we'll talk about is the fact that water participates in various chemical reactions. You may be loosely familiar with the term pH. So let's talk about what pH is. There is something called a pH scale. The pH scale basically is just the measurement of the amount of concentration of hydrogen ions in a solution. Plain and simple. Most of the chemical reactions within the cells within our bodies as well as in cells of certain other living organisms generally operate around a pH of 7. 7 is considered neutral pH. The pH scale goes from 0 to 14, which 7 being midway the scale is considered neutral reading for pH. And we're going to talk a little bit more about that, but this is just to give you an overview. Anything with a pH less than 7, 6, 5, 4, 3, 2, 1, is considered an acid or to be acidic. If the pH of a substance is above 7, then it is considered to be basic, a base. Remember, when we're talking about pH, we're talking about the concentration or the amount of hydrogen ions that are present in whatever the substance or solution is that we are talking about. So again, the pH scale shows the amount of hydrogen ions that are in a solution. If in fact the solution is an acid or is acidic, it has a low pH. So in other words, a pH value of less than 7. This indicates that there is a high concentration of hydrogen ions. On the other end of that scale, you have basic solutions that have a high pH value. In other words, the value is above 7, so 8, 9, 10, all the way up to 14. These solutions have a low concentration of hydrogen ions. These are considered bases. Now, what we see is these bases have more of an OH ion than the hydrogen ions. This OH minus that you're seeing on this slide is referred to as a hydroxyl group, HYDROXYL, hydroxyl. When we return to class, I'll go over this a little more because I feel that I can explain it better on the blackboard as I'm talking to show the association between hydrogen ions and hydroxyl groups, especially when you talk about splitting of bonds of water to form your H and OH. But know that basic solutions have a higher concentration of this hydroxyl ion or OH minus, whereas acidic solutions have a higher concentration of just the hydrogen ion, H plus. So when we look at the molecular structure of water, H2O, and those bonds become split, forming a hydrogen ion, H plus, and the hydroxide ion or hydroxyl group, the OH minus. Again, that's when we start looking at or can get a better feel for, concentrations in terms of the amount of hydrogen that is present when speaking of that relative to pH scale. Now, when we break down a water molecule, break down the amount of hydrogen and the amount of hydroxide ions in a solution, we again get into concentration amounts of hydrogen ions as opposed to hydroxide ions. If the hydrogen ions, H plus, equal the concentration or the amount of hydroxyl or hydroxide ions in a solution, that's when we get a neutral solution, so that pH of 7. So you have a balance between acids and bases. Therefore, that solution is neither acidic or basic. It is considered neutral. pH is 7, which means the concentrations are equal in terms of what the concentration of hydrogen ions are relative to the concentration of hydroxide ions. In acidic situations, you have a higher concentration of hydrogen ions. So hydrogen ion concentration is greater than hydroxide ion concentration. In basic solutions, the hydroxide ion is what prevails. So the hydrogen ion concentration is less than the hydroxide ion concentration in basic solutions. So in many solutions or many reactions, chemical reactions, we need to maintain a pH of 7. So this neutral pH, this homeostasis, if you will, in terms of chemical solutions, that pH of 7. There are solutions called buffer solutions that help maintain a constant pH by either absorbing or releasing hydrogen ions into a solution. Again, we're not going to get heavy into it because I don't want to turn it into a chemistry class. It's beyond the scope of my knowledge. But know this, there are solutions called buffer solutions that can be added to a solution to help bring it back into homeostasis. If it's too acidic, then it may add some hydroxyl ions to bring it, closer to that neutrality, or vice versa. If it's too basic and we want to increase the hydrogen concentration, then the buffer solution would be one that would do that, contribute hydrogen ions to the solution. But the takeaway from this is buffer solutions are solutions that help maintain a constant pH by either absorbing or releasing hydrogen ions, depending on what the preference is or what is needed for a particular reaction to go forward or for a solution to be brought into homeostasis before it is used. And this is just another look at the pH scale, but what this particular slide is pointing out is that each pH unit is 10 times the difference in terms of hydrogen ion concentration. So the neutral pH of 7 is actually like 10 to the 7th power. So again, just to, put things into perspective, simple numbers are used when we start talking about, the pH scale 0 through 14, but know that those numbers actually are 10 raised to that power. So again, it's 10 times the difference from one step to the next, or one step on the scale to the next. So now let's kind of shift gears and we're going to talk about organic molecules. Now, that word organic can mean a lot of things in terms of layman's terms, but when we speak of organic molecules, we're talking about substances that contain carbon and hydrogen. Within our bodies, there are various organic molecules, but we're going to talk about four major types of organic molecules. Since those molecules, yes, they are chemical in nature, but they are also biological in nature. So they're in essence biological molecules, and we truncate that word, and instead of saying biological molecules, we just say biomolecules. So the four major types of biomolecules, which are organic molecules that are very relevant to the workings of the biochemistry of our bodies, are carbohydrates, proteins, lipids, and nucleic acids. So again, when we speak of organic versus inorganic, organic compounds generally contain carbon as well as hydrogen. Now, there may be other types of molecules bound as well, but certainly those two elements we will see in an organic molecule. We will see carbon and hydrogen, oftentimes carbon and hydrogen bound to each other. But again, that does not mean that other elements are not involved in the compound as well, as opposed to inorganic compounds, most of which contain other elements besides carbon, but there are some that do contain carbon as well, but generally there would not be hydrogen. So if carbon and hydrogen are both present in a molecule, it is considered organic. Now, if it only contains carbon or only contains hydrogen in addition to other types of elements, then it is not considered organic. So again, it can be inorganic and contain carbon, but if it does, then it means it probably does not contain hydrogen. Because by definition, or our definition, organic is going to be a compound that contains both carbon and hydrogen in addition to other things that it may contain as well. So just to drive that point home, organic molecules. An organic molecule is a molecule that contains carbon atoms, generally bonded to other carbon atoms as well as hydrogen atoms. And these organic molecules tend to be very biologically important for many of our life functions. So, the biologically relevant organic molecules or biomolecules that we will now discuss are carbohydrates, lipids, proteins, and nucleic acids. So most of these organic molecules or macromolecules, macro meaning large molecules that we're going to talk about, are actually made up of repeating units of a single type of molecule. These repeating units, we're going to refer to them as building blocks. And another term we're going to use is monomer. So mono meaning one or singular. So these monomers will join together to form polymers. So you're going to have several individual building blocks or single units, which we're going to refer to as monomers, that will come together to form a polymer. So a single unit macromolecule, large molecule, which we're still talking about these organic biomolecules, that they can be broken down into individual units. Just as we talked about, say, tissue being broken down into individual cells. And so, therefore, our individual cells, say, for instance, our individual skin cell would be a monomer for our skin tissue. So, all of these individual cells or individual monomers have come together to form a polymer. So, something made up of many units. Likewise, with these biomolecules, that we're about to talk about, they have individual building blocks or monomers that come together to form whatever that unit is, be it a carbohydrate, lipid, nucleic acid as a protein. And they all have their very specific monomers, their very specific building blocks or individual single units that come together to put a lot of these monomers together. So when a bunch of these individual units or monomers come together, they form a polymer, but these polymers have different names depending on what they are or what their building blocks are. So there's a process called dehydration synthesis that is used to join these various monomers together in order to form a polymer. So again, we know that water is very important in various chemical reactions, or the water molecule is important in various chemical reactions. In this process of dehydration synthesis that joins individual monomers, individual units together in order to form a polymer, water molecules are actually removed from these monomers in order to create bonds to form polymers, regardless of what the polymer is, because remember, polymer is just a generic term, meaning there are various monomers that come together in order to form this larger unit, which is a polymer. Polymer could be a protein, it could be a nucleic acid, it could be a lipid, etc. So when we talk about these organic macromolecules, the carbohydrates, the proteins, the lipids, etc., and the fact that they are themselves polymers. So carbohydrate is a polymer that's made up of a specific type of monomer. Protein is a polymer that's made up of a specific type of monomer. Lipid is a polymer. A nucleic acid is a polymer that's made up of its, specific units, and we'll talk about what the monomers are for these various macromolecules. Know this: just like these monomers can come together, and they come together by connecting via bonds, okay? Well, guess what? Those macromolecules or polymers, they also can be broken down back into their individual units, so into their monomers. Now, there's a process called hydrolysis. So when we look at that word hydro, Hydro, that lets us know that water or water molecule is in some way involved. When you see the word lysis, or that suffix lysis, Lysis, lysis means to split or to break down. So lysis, Lysis, means to split, break down, break apart. So that word hydrolysis or hydrolysis, but hydrolysis means to break down something or to split something using a water molecule. So in this process of hydrolysis, and I think your chapter really does a good job of explaining it, so please refer to your chapter. What will happen is water is actually used, or water molecule is used to break the bonds between individual monomers that are part of a polymer in order to now form just those, or break down to those individual monomers. And there are times that we need that to happen. When we talk about metabolism, there are different components of metabolism. Metabolism is part of a big process. So you've got catabolism, which is the breakdown of, certain macromolecules to get individual molecules to extract units. But then you have anabolism, which is the building or putting together uh, of um, of molecules. So again, there are times when our body needs to break down large molecules in order to reap the benefits, and there are times when we need to build macromolecules or polymers out of these monomers. Water is so essential, or the water molecule is so essential to so many functions that occur within our bodies. So, in the case, in part of our metabolic processes of breaking things down and breaking bonds in order to utilize maybe the monomeric unit of something, the process of hydrolysis or bonds being broken down by water is very, very important to many biochemical processes within our bodies. So when we talk about these various biomolecules, carbohydrates, proteins, lipids, etc., I guess the big question is why? What is the significance? What is the relevance to us? These biomolecules oftentimes are very important, well, not oftentimes, all the time, are very important for the workings, the biochemical processes to occur in our bodies, for us to obtain energy for various processes and functions to be performed within our bodies. Now, we're all familiar with the word calorie. We look at the scientific definition. Calorie is the amount of heat required to raise the temperature of 1 gram of water, 1 degree Celsius, which means absolutely nothing to me, which is just like, okay, and what? But when I look at the second part of that, it says that a calorie is an amount of food having an energy producing value of 1 large calorie. Okay? So now it's starting to make some sense, or it seems to have some relevance to me. So when we talk about these various biomolecules or macromolecules, how does that all fit into the grand scheme of things? We know that various foods have carbohydrates and proteins and fats in varying amounts. We have all kind of gotten into reading nutrition labels on foods to see how many calories it has. And I know I've had the question in the past, how do they come up with this? How do they know how many calories are in this particular type of food? Well, they have a formula. They have figured it out. They have determined based upon research, test after test, as to how many calories are in a particular type of macromolecule based upon weight. So, in terms of carbohydrates, carbohydrates provide 4 calories per gram. So, weight of the food or substance. Proteins provide 4 calories. Fat accounts for 9 calories. If you look at the nutrition label, this particular food product, whatever it is, says that it contains 230 calories. Well, how did they come up with that? So what they did was they looked at the total amount of fat that's in this food product, and they said, okay, based upon the science of it, fat provides 9 calories. So if there are 8 grams of fat in this particular food product, and we multiply that times 9 and get 72, we get 72 calories just from the fat. Likewise, we look down and we see, okay, total carbohydrates are 37. Multiply that times 4 because carbohydrates provide or contribute 4 calories to this food. And I think that number is like 148 or something like that. And likewise, protein provides 4 calories per gram. There are 3 grams of protein, so 4 times 3 is 12. Add them all together. I think when you do the math, it's about 232. So plus or minus, this calculation is how. Therefore, if I were to give you a nutrition label on your exam and you had all of these facts, plus, of course, I wouldn't expect you to necessarily memorize. You'd be given the information, but you do need to be able to perform some simple multiplication and addition. You could now calculate the amount of calories in the food product that you're given if you know the total carbohydrates, proteins, and fat. The other minerals that are involved do not contribute to the calories, which is why they're not included in the formula. You notice that there is 160 grams of sodium. Well, that's not included in that caloric formula, but just the carbohydrates, the proteins, and the fats. And quickly, this is just a table that you can take time to look at for yourself, but just to re-emphasize that, many of these organic or all of these organic molecules that we need in terms of the functioning of our body, we consume via our food, or we consume it or obtain them through taking various supplements. Um, each of these biomolecules do have monomers that they're made from, and this table just basically breaks down some of the molecules. So let's take a closer look at these biomolecules. First, carbohydrates. Carbohydrates will include the elements carbon, hydrogen, and oxygen in the ratio shown 1 to 2 to 1. Carbohydrates are used for energy storage and to get quick energy. The monomer, or the specific building block individual unit that make up carbohydrates, are our simple sugars. These simple sugars are called monosaccharides, such as glucose. They are a simple single sugar. Monosaccharides are, again, just a single unit, glucose. But if you have two sugars put together, then that is a disaccharide. Multiple sugars put together is a polysaccharide. It is also called a complex carbohydrate. Your book goes over this very well. This slide just shows different types of monosaccharides, so simple sugars, glucose, fructose, galactose. And again, these monosaccharides can be joined together, multiple units of either an individual monosaccharide, like many glucoses coming together to form a polymer or polysaccharide, or you can have different ones joined together, but again, in repeating units, depending on what it is you're trying to form, what type of polymer you're trying to form. So again, disaccharide just means that they're repeating units of two sugars that have been bound together. So sucrose is a disaccharide that is formed up of glucose and fructose. Lactose is a disaccharide. It has two sugars, the lactose and glucose. Maltose, it is also a disaccharide, but it is repeating units of just two glucoses formed together. But again, the monomers are the individual units, and when these individual units come together repeatedly, making repeating units, via bonding, then they become polysaccharides. Again, if it's two sugars, it is a disaccharide. One sugar, simple sugar, monosaccharide. But then when you have many of these units put together, many of these saccharide or sugar units put together, forming a complex carbohydrate, now it is a polysaccharide. So again, a polysaccharide or complex carbohydrate is just long chains of carbohydrates. They're often used to provide support, say for instance, cellulose in plant or chitin in fungi. You also find chitin in the exoskeleton of insects. Polysaccharides oftentimes are used to store energy. So in plants, you can see polysaccharides in the form of starch, but in animals, you see polysaccharides in the form of glycogen to store for energy. So for instance, we have glucose and we use glucose for energy. That glucose, excess glucose is stored as glycogen within our bodies. The next biomolecule or macromolecule are proteins. Proteins are the worker bees of the cells. They do almost everything. There are so many functions that proteins are involved in. And as the semester goes on, we'll start talking about some of those functions in more detail. The monomers or individual units that make up proteins, because remember, protein is a polymer, which means it is made up of many units of something, of some sort of monomer. Well, the monomer that makes up the polymer protein are amino acids. There are 20 different amino acids of biological relevance. All amino acids have the same general structure. They have what's called an amino group and a carboxyl group and what is called a varying R group, and that determines what the amino acid is. We'll talk about that later on in the semester. But just know that the monomers or building blocks for proteins are amino acids. So it's stated there are 20 different amino acids. Okay, they have different R groups. Some are polar, which means they have charges. Some are nonpolar. Some are charged. Some are small. Some are medium. Some are bulky. So just various size, and they have various properties. And based upon the size, the properties, configurations, that determines what type of protein will be made. Because again, there are all types of proteins used for various things throughout our bodies, and we will learn more about that as we progress in the semester. So, a few slides back, I talked about hydrolysis and breaking down using water molecules to break down these polymers into their individual monomeric units. But one thing I didn't talk about was when we combine these monomers. The process of combining or being able to cause some of these bonds to form when forming these polymers is called dehydration synthesis. Dehydration synthesis binds two amino acids together to form or via peptide bond so that you can now form these polymers as opposed to hydrolysis, which actually separates the polypeptides or these polymers, polymeric units of proteins. So again, the hydrolysis would break down the polymer, or the polypeptide, or the protein into its individual monomers, which are the amino acids. But those individual amino acids can be brought together via a process called dehydration synthesis to cause these bonds to form and now build these polymers. And of course, in this particular case, the polymer is the protein. Understand that when I say polymer, polymer is just a very general term. I can say dog, cat, apple, whatever. But unless I've told you what type of dog it is, it can be a Chihuahua, poodle, whatever. It's a dog. That's a general term. Polymer is a general term. So we need to know what polymer we're talking about. Are we talking about protein, which is a polymer made up of many monomers of amino acids? Are we talking about some sort of carbohydrate, which is a polymer made up of many monomers of, say, sugars or monosaccharides? So again, just know that the word polymer is actually a very generic term because there are very specific types of polymers. A polymer, again, is just something made up of many monomers or monomeric units. Now, as with almost everything in our body, we talked about life, that there is a hierarchical or organizing, if you will, and that there's specific structure. Things are not just kind of randomly thrown together. There is actually a very specific structure and hierarchy to how our bodies are put together. Well, likewise, there's a structure and hierarchy and various types of structures to how, different macromolecules, most specifically proteins, are put together. Proteins, again, are polymers made up of monomers. The monomers that proteins are made up of are amino acids. There are different types of proteins within our bodies. They have different functions. Depending on how this protein, number one, depending on what monomers make it up, what specific amino acids make it up, that will determine what the protein is, what type. Is it a protein, um, an antibody in our bodies, or is it, one of the proteins, in our muscles? It's one thing to determine what the protein is, but we also need to know that that protein is functional and will do what it was formed to do. So the primary structure of a protein is just that whole sequence of amino acids, those monomers put together. But then you have what's called a secondary structure. So that's how that whole string of monomers are folded. And you have two primary configurations for that folding or secondary structure of proteins. You have what's called the alpha helix, and you have the beta pleated sheet. These are very specific folding configurations. These are very important because depending on how that protein is folded and that it is folded properly, that determines whether or not it is going to function and do what it was designed to do, perform the task it was designed to perform. In addition to the primary and secondary structures of proteins, there are also tertiary and quaternary structures. The tertiary structures are just those secondary structures, either the alpha helix or the beta pleated sheet folding back on itself. But the quaternary structures, when you have like a couple of separate sheets that interact and fold on top of each other, now making the entire structure. But again, all this folding, be it at the secondary level, tertiary level, or quaternary level, determines whether or not the protein will function and perform the job that it was dedicated to perform or designed to perform. So again, the structure, the folding of the protein determines whether or not that protein will be function, what its function is. The function of a protein depends on its structure, so that whole folding process. If in fact it is not folded properly, then it will not function properly. And there are different things that can cause, even if the protein is folded properly and it's functioning like it's supposed to, there are things that can cause these proteins to become unfolded or their folding to be distorted in some way. When proteins are not folded or structured the way they're supposed to be, then they are said to be denatured. So look at that second bullet. Denatured proteins lose their shape. So they no longer have the folding shape or structure that they're supposed to. And when they lose this particular structure, the way they're folded or not folded properly, we say they're denatured and they don't function in the same way anymore. So this denaturation of a protein is just the loss of its shape or structure, which means its function changes as well, or how it functions. Different things can cause denaturation of proteins, can cause it to unfold or to misfold. Excessive heat, excessive salt, changes in pH, so concentration of ions, or genetic mutations can also cause it. So again, in this particular example, we look at, this egg. The protein is functional. Now, the whole purpose of an egg is so that a new chick can be formed, okay, if we're talking about chicken eggs. So that protein within that egg is folded a certain way to support the life of another chicken, a baby chick. However, if now the protein within this egg becomes denatured, so it loses its structure, then it no longer will serve the purpose for which it was initially intended. If you think about an egg, if you crack an egg open and you're going to have you're going to have the white, and it has a specific consistency, right? But now take that same egg, don't crack it, but boil it. You can see the white and the yolk, but they've taken on a different consistency because the proteins now have either been refolded or the folding has been altered in some way. That boiled egg now cannot produce a chicken. Likewise, crack that egg, scramble it up. So once again, you have denatured that protein in some way. You have altered the folding, the structure. You scramble it, you definitely not getting a baby chick now. Okay. So again, things like heat can cause denaturation or unfolding or misfolding of proteins. And the egg is just one example, trying to give you a visual. Excessive salt can cause protein denaturation, pH changes, and genetic changes. Make sure you know what can cause denaturation of a protein. So, in other words, cause it to lose its shape. Also, make sure you understand that if proteins become denatured, in other words, lose their shape, be it that they were unfolded, misfolded, or what have you, if they lose their shape, if they become denatured, if proteins lose their shape and proteins become denatured, they also lose their function, what they were intended to do. They lose what it is they were primarily designed to do. They lose the ability to perform whatever the task is they were initially designed to perform. So if a protein becomes denatured, which means it has lost its structure, it also loses its function. It loses its primary function. And the four key ways that we're talking about, there are other ways, but the four primary ways that we are discussing that can lead to protein denaturation is heat, excessive salt, pH changes, and genetic mutation. Next, we will talk about lipids. Lipids are said to be hydrophobic, which means they hate water. Remember, phobic or a phobia, or have a fear of water. There are different types of lipids. There are triglycerides, which are your fats and your oils. They can provide, long-term energy storage. You have phospholipids, which means you have a part of it. They have a phosphate group involved. You see phospholipids in the membranes of your cells, and we'll talk about cell membranes when we talk about the cell in more detail in chapter 3. And then you have steroids. Triglycerides, again, fats and oils, they're made up of monomeric units, but theirs are a little bit different than we see of just like repeating units of monosaccharides and carbohydrates and amino acids and proteins. They're made up of three fatty acid molecules joined to what's called a glycerol molecule. Dehydration synthesis will link the fatty acids to the glycerol, and then hydrolysis can be used to separate those fatty acids from glycerol. So there are different types of fatty acids. You have saturated fatty acids, all the carbons are bond together to four other atoms, forming basically a straight structure, as opposed to unsaturated fatty acids, which contain at least one double bond and it's bent. And because of the physical structure of the unsaturated fatty acids, this prevents them from packing close together. And you see this with liquid oils. We also was we also have what's called trans fats, which is a form of unsaturated fat. So you have artificial trans fats. This process adds hydrogen to vegetable oil to form a solid known as partially hydrogenated oil. And this whole process allows for a longer shelf life, so an extended expiration date. This can also increase your bad cholesterol, your LDL, and you see a lot of trans fat in certain baked goods, snacks, fried foods, etc. You also have steroids. Steroids are an important type of lipid molecule, and we see that in the membranes of many of our cells. Nucleic acids are another type of biomolecule or macromolecule. Nucleic acids, we know, carry genetic information, and there are two types of nucleic acids. There's DNA and RNA. I'm going to kind of gloss over this very quickly because I want to spend some relevant time on it when we are actually in class. But the amino acid sequence of each protein in a cell is determined by nucleic acids. The monomers that make up nucleic acids are called nucleotides, and there are three parts or three components that make up a nucleotide. You have the phosphate group, you have the 5-carbon sugar, and you have nitrogenous base. Now, depending on whether or not it's RNA or DNA, it's a different type of 5-carbon sugar. RNA, which is ribonucleic acid, has the 5-carbon sugar ribose, R-I-B-O-S-E, whereas DNA, deoxyribonucleic acid, has the 5-carbon sugar called deoxyribose, D-E-O-X-Y-R-I-B-O-S-E, and you can refer to your text. And this slide shows those two sugars that I was talking about, deoxyribose for DNA and ribose for RNA. The other component that makes up these nucleic acids are nitrogenous bases, adenine, thymine, cytosine, guanine, and uracil. These nitrogenous bases actually bond to each other in very specific ways. And again, when we're in class, I'll talk about them a little bit more because I kind of like to draw those out on the board. I just think, it explains and it comes across so much clearer to see it in action. And this whole phenomenon of these nitrogenous bases bonding in very specific ways is called complementary nitrogenous bases because adenine always binds to thymine or uracil, cytosine always binds to guanine. Now know that thymine is only found in DNA and uracil is only found in RNA. Again, I will go over that in more detail or at least restate it when we're in class so that we can have a little more discussion on that. But again, refer to your text, it explains it very well. This slide is just giving you, again, another perspective of this complementary pairing between these nitrogenous bases. These nitrogenous bases also have categories purines and pyrimidines, and again, we'll discuss that when we return to class. So the two types of nucleic acids are DNA and RNA, and they are long chains of monomers called nucleotides. So the monomers for the nucleic acids DNA and RNA are nucleotides. And this table again just gives you an overview of those macromolecules that we're talking about, their chemical structure, and the functions of each, what their primary function is or key functions that are most certainly relevant to us. So again, you can take a few minutes just to review and go over this particular slide. And that's all for today, folks. I hope to see you all in class next Tuesday. A few of these points that I went over, I will review them as well. I'll spend just a few minutes on them and then we'll move on to chapter 3. But if you have specific questions after studying, you most certainly can ask them in class, but know that there will be a quiz over chapter 2 when you come to class on Tuesday. Stay safe, be warm, and have a wonderful weekend.